Good morning, all. Greetings from SEDSK City. It's a pleasure for me to welcome you all to Cosmonaut 2020. A small information about the certificates. Feedback form will be posted in the chat box at the end of the session. Certificates will be provided for only participants who fill the form. I again welcome you all to Cosmonaut 2020.
A happy morning to one and all present here. Astronomy compels the souls to look upwards and lead us from this world to another. Are the words of the great philosopher Plato.
Yeah, thank you. So if at all at some point in time I'm not audible, please let me know. So thank you for that introduction. So I'll just tell a little bit about what I do. So I'm a science communicator and science educator. I teach students, not college students, of course, school students on astronomy, and also educate public on science, popularizing science among the public. And my area of interest is in astronomy, physics, and mathematics. So glad to be talking to you all today. Before I begin my session, I would like to know if you can in some way let me know what the audience, like, are you a schools? Some of you might be school students, some of you might be college students. You will just let me know who you are in the chat box so that it will give me an understanding of the diversity of the audience. Possible? Okay.
So most of them are from colleges only.
Most of them are from colleges. Okay. So I just wanted to talk accordingly. Okay, thank you. So I assume most of you are college students and have good understanding of physics, the basics of physics as well. So today's talk is going to be on this story of gravity. I remember as a student when I was in sixth grade or seventh grade, I came across this very famous law of Newton's, law of universal gravitation. Every body attracts every other body with a force that is proportional to the product of the masses and inversely proportional to the square of the distance between them. This was a definition that I had to memorize in order to get 2 marks or 3 marks, whatever that answer demanded, and that was about it. I hardly enjoyed it. I didn't know what it meant actually, but all I knew, I still remember to this date, word by word, what that definition stood for. Not just the universal law of gravitation, but also the laws of motion that Newton said, the three laws of planetary motions and the equations. All of them, including the definition of force or gravity, whatever it was just a mere sentence. There used to be like a couple of sentences on the book, and we read it. We either understand it or not. We score good in the exams and we move on to the next higher grades or into the college. So it was not until after the college, it was not until I started teaching students. So I started my science teaching in the year 2013, about 7 years ago. So once when I started teaching students, that is when I realized, oh my goodness, this is not, I don't understand this clearly either. So I started putting efforts to understand something better. Particularly since I was interested in physics, I started putting more efforts in understanding physics so that I can teach my students better, or even in the case if they have questions, I'll be able to answer them. So I was on a journey to understand these things better. So every time I approached any topic in physics or astronomy, I was always, drawn back to the history of it, like what came before that, what was going on in the minds of people who came up with such ideas. So who was the person who was studying it before this particular scientist or expert. So it actually led me on a journey, not just for the topic of gravity, but almost in all topics in physics. I was just thrown to this entire journeys of various scientists and people involved in before it can come to us on the book, 2 lines can come on the book, what went on before those 2 lines could be written on the book. So that was my inspiration. And since then, I've been hooked onto it, and I've been teaching my students on the history of astronomy and physics as well, not just the concepts. So now today, I'm going to talk about one such a topic that I always enjoy, and I'm sure you will be interested in as well, is the story of gravity. The reason I'm talking about story of gravity is to teach you how science itself has evolved over time. Like, we have scientific theories. I'm sure since you guys are from college, you know what is a hypothesis, you know what is peer review, you know what is experimentation results, all of that. So now, not science did not have this rigorous method always. We eventually had to move on to a more rigorous method, which we have followed today. So now, through this story of gravity, it is my hope that you understand how understanding gravity actually shaped the method of science also, the what we so-called the modern science. Of course, the modern science is a terminology that we use to refer to the refinements in the method of science. Okay, so that is closely related to the story of gravity. So hence I picked up this particular concept. So yes, so this is going to be a story. So I would love to take your question. It would be great if the questions could be asked at the end of my story. It is not a concept-based technical session where you will need to ask questions then and there. So even in the case if you have any questions, even during the story, just let me know in the chat box. I think one of the organizers can read it out to me so that I can answer them. So now let me share my screen. I'm allowed to share, right? Okay, just give me a moment. Is it visible, my screen?
No,
Is
sir.
my screen visible?
No, ma'am.
No, sir, not it.
Okay. Just give me a moment.
Yes, sir.
Could be some issues. Okay, let me know once you see it so I can start.
It's visible, sir.
It's visible? Okay, so thank you. There might be some disturbances in my voice because of my poor internet connection, but as long as I'm audible and clear, please bear with those minor disturbances that you may face when I'm talking. So this story that I'm gonna pick up a mystery object, like since most of you are in college, this particular talk was also aimed at public at large. So some of you may eventually identify what this object is or may already know what object is. This is just a key in the just a key element in this entire story. It is not important whether you find it or not, what this object is. So this mystery object is what I'm going to base my story of gravity on. So now we are taken to this year, January 1684 AD, and it is a room. It's a coffee house, probably somewhere in United Kingdom. And there were 3 people in the room discussing, very seriously discussing on a problem. I'm sure most of you know these names. Edmund Halley, he's a very famous astronomer. He's not just an astronomer, he's known for his work on various other scientific disciplines as well. For example, meteorology and charting the maps of things. So he was known for that. And then we have Christopher Wren, who was also an astronomer, but he was also a very famous architect. So he was known for being the architect of a lot of churches like St. Paul's Cathedral, and is very famous architect. Okay, and we have Robert Hooke, and I'm sure you have heard of Robert Hooke, most famously known for his Hooke's law of elasticity, and he also, of course, he was the first person to observe the microorganisms through microscopes and also even coined the term cell. So they were all interested in astronomy and how the planets and orbited and things like that. So now they were in the early months of 1684 January, they were discussing on some very serious questions. This happened nearly 336 years ago from today. So yes, and I'm not going to tell you what was the question that they were discussing about, but just I want you to remember this date, 1684. So now let's go back Now I'm going to take you further back in time and eventually come to this particular date, Jan 1684, to reveal what the question was that they were discussing. So now humans have always been curious about nature. Okay, that there are, and one of the things, human civilizations have been around for more than 10,000 years. So before, until 10,000 years ago, we were nomads, wanderers, and hunters and gatherers. So humans never really settled down in one place, to have any sort of a free time or a comfortable time, a space where they could feel protected to think about the nature. So for most part of the time, the very survival of humans were a big challenge. And of course, the average lifespan was much lesser, maybe 20 or 30 back then. So now, once humans started settling into civilizations, they were able to bring the food to them. Earlier, they went in search of food. They were hunting for food. But with the civilization idea in the frame, they were able to bring the food to wherever they were. So they no longer had to, wander. So that was one big step in humans being able to think about a lot of other things. Then, of course, they had formed civilizations. They had a structure. They had a protected area where they could keep the animals and whatever their prey could be. So now, once that happened, humans slowly started thinking about the nature around them. I'm not denying that even before that, humans wouldn't have done that, but a more structured way of thinking about nature, or more of curiosity, was kindled. It's during once a civilization idea settled in. So now there are so many people involved, but I'm just going to pick up some very important names who thought about the heavens, as they called it back then as well. What are the things that you look at the sky? When you look up at the sky, there are hundreds of stars. At least back then, they should have seen several hundreds of stars, because the sky would have been more clear with lesser light pollution. So they naturally wondered, so what are these lights? Some of them twinkle, some of them don't twinkle, some of them are bright, some of them are faint, some of them moved across the sky very quickly. There were so many other events that happened, and naturally people wondered about them. So one of the most pivotal figures that all of us know is Aristotle, and of course Ptolemy as well, Ptolemy. So Aristotle and Ptolemy, in their view of the world, or I would say the view of the universe, they conceived of a universe which had a natural order. Okay, according to them, the nature was made up of four elements: earth, water, air, and fire. Earth, water, air, and fire. These were the elements that the entire universe was made up of, and they all had their own natural order. When I say natural order, it was that earth will, being the heaviest of all, will be at the bottom, and water will be above it, and air will rise above water, and smoke or fire will rise above air. So this was the natural order, like earth, water, air, and fire. So again, their view of how things moved was that each of these element will find its own natural position or space in this, according to this order. So earth will naturally be at the bottom, water will naturally rise above the land, and if there was air, even if the air formed underwater, in the form of bubbles, it would come to the surface and escape. So natural position of the air was to rise above water. And fire, like as they all visually saw things, fire, smoke even rose higher than the air. So that was the natural order, and that was their explanation of, sort of, you can say, gravity. Of course, back then they didn't know of the word gravity, but that was how things settled according to their position of the natural order. Now, the second view, which was again one of the famous things that Aristotle is known for, is the geocentrism model, where he placed Earth at the center of the entire universe, and also it is immovable. So the entire things that you see in the sky, the stars, the planets, or anything that you see in the sky, including the moon and the sun, it all moved around the earth. So that was a geocentric model that Aristotle was known for, and also Ptolemy, who came after him, also in his book Alchemist, he also came up with geocentrism model. Okay, now there are other people like Aryabhatta, I'm sure you have heard of him, and other Indian astronomers as well, who sort of came up with the idea that Earth could actually be spinning, and it was not the sun that moved, but Earth's apparent motion of the sun because of the Earth's spin. And also he was known for calculating and predicting eclipses as well. And there were other, of course, in every civilization, not just in Indian civilizations, it could be any other part of the world, wherever civilization existed, there are naturally few people who would have thought out of the box to challenge what was the conventional wisdom at that time. So Aristarchus of Samos was also again one who was in favor of heliocentrism. Aryabhatta, by the way, was also in favor of heliocentrism. Of course, all these are not concrete models that they had back then. No one had any sort of evidence to prove that sun was at the center. So the widely accepted model back then was geocentrism because that was easily believable, or that made more sense, because we don't sense the earth moving, we don't sense the earth spinning, but we always see the sun moving, rising up and setting, and all the other stars rising and setting. So it was natural to anybody to accept the geocentric view of the world, which was Aristotle and Ptolemy was known for. Now, there were a few problems. Like, no, it's not that Aristotle and Ptolemy were right and everything that they observed matched with their model. There were a few problems in their model of geocentrism. It could not explain every star in the sky or every point of light in the sky. So one of the things that way back then was popular, was even today it is popular, is astrology. People wanted to predict things based on the position of those points of light you see in the sky. So one of the challenges of the astronomers back then was to predict where each point of light would move in the next day or the next month. So the prediction of the movement of the point of lights was a very big challenge. It is only if you could predict those motions correctly, you can predict the astrology or horoscope more correctly. So now, out of all the stars, there were some points of light that did not fit into the geocentrism model, or rather I should say, they were not able to predict their motions precisely. The predicting those points of lights were more difficult. Okay, of course, we know that those are planets. Planetes meaning wanderers. So those 5 points of light, Mercury, Venus, barring Earth, Mars, Saturn, and Jupiter, were visible to the naked eye, and those 5 planets were not falling into the natural explanation of what Aristotle and Ptolemy gave. So of course, they overcame the problem with something called as epicycles. Okay, what we call as those planets will themselves have a circular spin. Apart from going around the earth, they themselves go in small circles around an imaginary center. Okay, they hope that this explanation will somehow explain the way that they moved, and they tried to predict where these planets would be next based on the epicycle theory. Okay, again, that was the notion that back then. But Aryabhatta and Aristarchus of Samos, though they had these philosophies and ideas, they could really not come up with any mathematical model or any way of proving that their idea was equally valid, because it was more challenging for people to accept it. So now this was the very early understanding of the solar system, and also the very early understanding of the gravity, like everything had a natural order. Okay, so now from 4th century AD, okay, we call for the next 1500 years or the next 1100 years or 1200 years, not much changed in terms of changing the view of geocentrism to heliocentrism. Okay, so you can imagine, for most part of for nearly a millennia, geocentrism view of the world was popular. That was widely accepted. Even though today we know that it is not the case, but nearly for 1,000 years, that was the belief, widely held, accepted view of the world. Now, it wouldn't be until 1510 that Nicholas Copernicus, I'm sure all of you know of these names, but I'm just giving you a very different perspective of what went on with so many other scientists involved. Okay, it wasn't until 1510 that this view was squarely challenged, or Ptolemy and Aristotle were like upfront challenged with the ideas of Nicholas Copernicus. He came up with this heliocentric model of the solar system. So now it is all the historians or the scientists agree that there is no clear indication of why Nicholas Copernicus was favoring the heliocentric model? What made him, what was the thought process that went on in his mind that he would reject Ptolemy and Aristotle's view and come up with this heliocentric model of the solar system? So now it is widely believed that it was the epicycle, the concept of epicycle or equants, if some of you are aware of that. That concept made Nicholas Copernicus very, very uncomfortable. So he was like, to explain the motions of objects in the sky, the theory had so much of complications. You had to make epicycles, and the epicycles also have to change the center of the cycle a little off from the actual center. There are so much of complications. Just to explain what is going on in the sky, also in view with the beliefs of the religion, or back then the church or the Bible, that very clearly stated that Earth was the center of the universe because the gods created it that way, and you cannot challenge it. The very widely held belief that Earth has to be the center, it has to be the most important thing in the universe. That notion, that small idea, made this geocentric view stand out for more than a millennia, and that made Nicholas Copernicus very, very uncomfortable. No, it cannot be that way. So he just quickly moved away from the epicycle concept or the equant concept, and he said, look, if we put the sun at the center and make Earth as one of the planets among all the other planets and make them go around in circles, then all these concepts of epicycles and all these complexities that we have to put in the geometry to explain the motion of the objects can be done away with. Why do you have to break our heads with epicycles? We can just happily put sun at the center and all these problems will fit or solve by themselves. So this was the motivation that Nicholas Copernicus had before he came up with this idea of heliocentric model. Of course, it was in 1510 that he made a very small piece of writing or work that favored the heliocentric model. But again, back then the church and the state were not separate. They were almost like had huge influence over the functioning of each other, and it was very difficult for Nicholas Copernicus to come out with such a notion that would challenge the widely held belief of the church or the people at large. So he really did not publish it or think about publishing it. Then, of course, he would eventually go on to work for several more years to have better understanding of the solar system, of the planets. He, in fact, made observations of the planets. He recorded the positions of the planets to come up with his models. Of course, he still did not completely do away with the epicycles. He was still trying to figure out the retrograde motions, the apparent retrograde motion of the Mars planet. I'm sure you guys know what is a retrograde motion. It is an apparent backward motion, like in the sky. Normally the planets move from west to east, drift eastwards through the year, and for a brief moment of time they move westwards and then resume their eastward direction again. So the apparent looping of the planets in the sky was something that could not be explained, and Nicholas Copernicus, he thought if the Earth moved like in an orbit that is closer to the sun, then this could apparently be eclipse, but still that was an area where still he was not very clear about. So as you can see on the picture to your right, he made all those orbits to be circular. Look, he made all the orbits to be circular. It's a slightly elongated image. I just stretched it in the y-axis so it looks elongated, but he made the orbits circular. Okay, so that was his model. Now, in 1531, there was a very another famous astronomer called Petrus Epianus, who observed the mystery object that you can see, that you see in the sky. This was the central talk of my story today, which I introduced you in the very first. So some of you may actually recognize this object, but either ways. So 1531, this object was sighted. So German astronomer documents this object. So 1510. So after nearly 21 years, this object is sighted. So first sighting of this object in our story. Okay. Now, in 1542, so now in a way Copernicus was very, very clever. I mean, I wouldn't say clever, but he knew that he was towards the end of his life. Like he died in 1543. So he was bedridden for a couple of years before that, I assume. So it was in 1542 when he was on his deathbed. He knew this was the time to publish the book, because even if the book is published and if there are rejections and criticism, and he wouldn't be alive to face those consequences because he would be dead anyway. So he thought that would be a right time to publish this book, and he published this book, translated into English as On the Revolutions of the Heavenly Spheres. And this is the book where he completely comes out his hypothesis of the heliocentric model, how the orbits would look like, where he publishes tables and the geometry of the orbits. So this was the book that one can very safely say that was the first that would create the first sort of a revolution. Okay, now I don't think it is a coincidence that we call any change, a major upheaval in the society or major upheaval in the political spectrum, we call a revolution, political revolution, green revolution, or the white revolution. So the revolution word itself, I think it had a huge reference to this particular book, which was actually on the revolutions of the bodies. So this actually revolutionized the way science would, the trajectory that science would take after this 1542, the book was published. It was not, this book was not an immediate matter of debate or public scrutiny immediately, but hardly anybody looked at it, hardly anybody read about it, and not rightly so. It was at that time, since nobody looked at it, people did not bother about what was in the books as well. It wouldn't be until 60, 70 years later that Galileo triggers this notion of heliocentrism again, that is, it will be taken seriously. But right after, in the few decades after the death of Nicholas Copernicus, the book was not making much of noise, and people really didn't bother, and it did not get the attention of the church that it later would deserve or later would get. So now this is a very important moment in the history where the book is published. So now, next we have another important character. His name is Johannes Kepler, 1596. I'm sure you know of any of you who took up science in your high school or higher secondary school, you would know of Kepler's laws. Kepler's law is also quite easy to remember. It's not one of those very complex laws to remember. So he, in 1596, he was a mathematician. Okay, Kepler was a brilliant mathematician of his time. He was he was like a mathematician apart, that would stand apart from another league of mathematicians. He was very good with geometry. He was very good with visualizing shapes, 3D shapes or 2D shapes. He was a very good math, and he was also working as probably he was teaching. It was a mathematical teacher as well. So he was also intrigued by the idea of a Copernican system. So where there were very less people who bothered about the Copernican model, there were very few who actually took interest in Copernican model, who would eventually go on to become the most pivotal names in the history of where we stand today. So Johannes Kepler was one of them, and he was on a journey to prove Copernicus right. Whether he wanted to prove Copernicus right or not, he was naturally hooked on to the idea of Copernicus, like placing sun at the center and making the planets move around it, and that was him. And now, before we move on to what Kepler was able to achieve, which I will eventually come to, the Kepler's laws of planetary motion, but there was another important character whom we are hardly talked about. Even if you look at your science textbooks, whether it's 6th grade or 7th grade, you know of Newton. Of course, you will know of Galileo, because these are very famous scientists. And of course, you would hear of Kepler as well. But this name, I don't think it's hardly mentioned. Even if at all this name is mentioned, it would be maybe one of the side notes, like one line or so. But he is one of the finest astronomers back then, and his data on the positions of the planets would play the most pivotal role for all of the other scientists to even come to the conclusions what they eventually come to. So he was also, again, like every other astronomer back then in the day, he was also caught up with the idea of the model of the solar system, whether it's a heliocentric model or a geocentric model. So though he was not comfortable heliocentric model with sun being the center, sun being the center, he was not geocentric model, the typical geocentric model. So what Tycho Brahe did was he came up with his own version of solar system. People called it, I think, geoheliostatic model. I think it's geoheliostatic model, or I think a more easier name to remember is the Tychonic universe. Okay, Tychonic universe he called it, wherein the two inner planets orbited the sun, and they, along with all the other planets, orbited the earth. Okay, so it was like other planets orbiting the sun, sun with all the other planets orbiting the earth. It was like ridiculously crazy. Okay, but somehow Tycho Brahe was sort of caught between moving away from completely moving away from geocentrism, at the same time not completely accepting heliocentrism. He's like was stuck in the middle ground. Partly it could be because of his religious notions, like he didn't want to completely move out of geocentric view, so still giving due importance to the planet Earth. So that was his model. But again, he was on a mission to prove his Tychonic version of the universe to be correct. So what he did was, of course, back then when Tycho Brahe was there, telescopes was not used. Telescopes was not there to record the positions of the planets. So he had to rely on his naked eyes to record all these observations. And trust me, he has recorded data for like decades, like 20, 30 years of data on various planets like Saturn, Mars, and Jupiter. So he wanted to collect, and also he wanted to reduce the error of his measurement of positions. So for those of you who know of how the angular measurement is made, it's measured in degrees, arc minutes, and arc seconds. Okay, so back then during the time of Tycho Brahe, the accuracy was up to 10 arc minutes or more than that. So which was quite, and predictions or fitting any model to those data. 10 arc minutes was still too big. So Tycho Brahe, it is thought that he's reduced the error margin by to around 1 or 2 arc minutes. So that was the level of accuracy that Tycho Brahe was able to achieve in his recording of the data of the celestial objects. Okay, so now again he collected all the data that he required for decades, but he was not able to somehow see that his version of the solar system, which is a Tychonic version, planets going around the sun together with the planets, all of them go around the earth, that could not fit the data of what he observed. Okay, now that is when Kepler was also interested in all these affairs, and he knew Tycho Brahe had all the data that he would eventually need to prove or to understand the motion of the celestial objects better. So I think it was in 1600 that they met, and Kepler, both of them, it's sort of both of them had their reservations about each other, but both of them could not help having each other. So it is like Tycho Brahe needed the genius mind of a mathematician like the ones of Kepler. The same time, Kepler needed the data that Tycho Brahe was holding, but both of them didn't get along well in terms of their understanding. For example, Tycho Brahe wanted Kepler to put efforts to prove the Tychonic version of the solar system was the correct, and that is one of the reasons he had Kepler as his assistant as well. But Kepler had other ideas. No, like, I just want the data, but I'm going to go into my own journey of looking at the Copernican view of the solar system. So, but again, as fate would have it, both of them did not work for long together because Tycho Brahe died in 1601. So in 1601, Tycho Brahe, I think he's dead because of some urinary infection, tract infection, and just 1 year into it. And in that 1 year before he would die, Tycho Brahe had given massive amounts of data on Mars. Okay, so Mars data was given to Kepler to study. The reason, it's very interesting, again, all these things, happened because of the emotions and what was going on within the minds of Kepler and Tycho Brahe. Tycho Brahe gave Mars's data to Kepler because that was the most troublesome data. Okay, Tycho Brahe found the data of Mars to be most difficult to fit into his own Tychonic version. Okay, because Mars had a higher eccentricity compared to all the other planets. Forget Pluto, but relative to all the other planets' eccentricity, Mars had a higher eccentricity. So the positions of Mars, the retrograde motion of Mars, was the data was more difficult to fit into the Tychonic system of universe. So Kepler, he was like, okay, Tycho Brahe thought, if I give this data to Kepler, I think this would keep him occupied for a long time. He wouldn't, get his nose into all my data and he overtake me in terms of understanding this. So that was his idea. It's like the data of Mars is in fact the most crucial set of data that someone would need to actually progress our understanding of the celestial objects, which Tycho Brahe thought otherwise. So again, I think just Kepler was just lucky, and Kepler got the data. And after his death, Tycho Brahe's death, Johannes Kepler had to fight with, I think, probably the family members of Tycho Brahe, and finally get his hands on the entire massive set of data that Tycho Brahe had made in the last several decades. So now, with this data in hand, he was able to make some great leaps. Now, it is also very interesting. Like, I always have been envious of such people like Johannes Kepler, because you were not only in the time where other great scientists were around, like Galileo, Kepler, and all the other scientists who lived in the same time, but also you get to see a lot of celestial events that we are not getting to see, at least in my lifetime. He observed in 1604, Kepler observes a very famous supernova called as SN 1604 supernova. It's called Kepler supernova, and it was shining at a very good magnitude. It was reportedly shining at minus 2.5. Sometimes I think it was even visible in twilight conditions during the daytime. So that was some of the things. Again, Kepler has had his own understanding of what supernova could be and things like that. These events were very important because even during Kepler's time, astrological significance was very high. So people observed these celestial events, and they connected these to various happenings of the world around them. So again, the supernova is a very interesting. This has nothing to do with the story of gravity, but it is still interesting to know that a supernova happened that was very bright, visible to the naked eye in 1604. And now, again, the mystery object, Johannes Kepler, in 1607, he observes our mystery object. Now, I assume you remember the last time this mystery object was observed. It was by a very famous astronomer, Apianus, in 1531. Again, Johannes Kepler observes this object in 1607. Okay. Now, in 1609, after working with Tycho Brahe's data for several years, now Johannes Kepler finally comes up with his famous laws of planetary motion, the first law and second law. I'm sure most of your college students who will know this. The first law simply states that the orbits of planets are an ellipse with sun at one of its foci. So the second law states that the planet sweeps out equal areas in equal time. This gave to the understanding that the planet will move faster when it is closer to the sun, and it will move slower when it is farther away from the sun. So this was the first two laws, but it's an interesting thought what went on inside Johannes Kepler's mind. Okay, like Copernicus, Johannes Kepler was also of the idea that the orbits were circular. Okay, I wouldn't say that he was just thinking that they were circular. He wanted them to be circular. Okay, circular was some sort of it is beautiful. Circle has a very unique kind of symmetry and geometrical symmetry, and circles were considered divine. Ellipses were not so divine. Like it looked like it's the works of a not so great creator. Circles would be the work of a great creator, but not an ellipse. So the obsession with the divinity of circles, okay, that actually bothered. Actually, that was crept into the mind of Kepler, that the data of Mars somehow could not be fit into the circular model. Also, he assumed, okay, there could be some errors. Johannes Kepler was of the idea that, okay, maybe there were some errors in the measurement of the data of Mars. So maybe that was the reason why it doesn't fit into a circle. If I account for some percentage of error, I could still fit it into a circle. But Johannes Kepler knew that the accuracy was very high. The accuracy of the data of Tycho Brahe was very high. And also he knew Tycho Brahe was very, very diligent in his measurement, that the error is very, very unlikely. So after years, like at least 5 to 6 years of struggling with his own sense of obsession with the divinity of circles and trying to fit the data that of Mars, he finally gave up. Like, okay, let me move away from my prejudice, my bias. Let me just accept the data as it is and let me fit a curve. Then he said, then he comes up with this ellipse as a model. The moment he changes, that's one shift of mind, like it's just a thought process, like, a mindset. The moment he shifted his mind from being a circle to being an ellipse, then everything fell in place. The data of Mars fit in so beautifully. He didn't have to adjust anything else. He didn't have to account for any errors. It just fit in so beautifully. Okay, so that was the first law, stating that the planetary the orbit of a planet is an ellipse. The second law, of course, concerned to the ellipse, the motion is so regular that the planet speeds up closer and it slows down when it's farther away from the sun. Okay, it was in 1609. Now, then around the same time, imagine these guys were living at the same time, like, Galileo and Kepler were around the same time. That was just great to know. But anyway, distractions aside, so Galileo, for the first time, he trained his telescope to the sky and he observes Jupiter's moons and the phases of Venus, he was also trying to see, he was also trying to favor Copernican model. So he does his observation of the Jupiter's moons that for the very first time revealed that not everything in the solar system moves around the Earth. It was actually the Jupiter and its moon itself is like a small solar system where it moved around. So that broke the divinity of Earth being at the center. That broke away from the that, like I told in the case of Kepler, happened as Jupiter's moons were observed by Galileo. He also made observations of Jupiter's moons to see if it fit with what Kepler and Copernican had to say. And of course, he observed the phases of Venus, which also added to validate heliocentrism. I'm not getting into much details of Galileo Galilei, what he did, but I must tell you here that Galilei's most famous contribution to science was that his ability to experiment to understand these things. So he knew that he wanted to understand about how things moved across the sky or how things moved on the earth, like a ball falling down, or there's a very famous legend that says he dropped a ball from the Leaning Tower of Pisa to know how long it takes for it to fall. So also he's known for the inclined surface experiments where he rolled down balls at different angles to study how long they take. So this experimentation to understand the way things moved on Earth was the most famous contribution of Galileo. And in fact, his understanding that all objects fall at the same rate, no matter if the ball is heavier or lighter, whatever be the case, all objects take the same time, they fall at the same rate, was one of the most important contributions of Galileo. And also he was he brought up the idea of inertia, and also he brought up with the idea of relativity, not the special theory of relativity, but the general principle of relativity. Okay, and that along with what would eventually become the conservation of energy and momentum. All those ideas would eventually stem from what Galileo did with those experiments. So that was his contribution in this regard for the gravity story. Now, it would take another 10 years for Kepler to come up with his third law of planetary motion, which I'm sure all of you know, we would have learned in your textbooks, that the square of the orbital period will be proportional to the cube of the semi-major axis. To give you a rough idea, the orbital period of Jupiter is 11 point some years, and the distance from the sun is 5 AU, I guess. So 5 cube is 125, 11 point something square is 122, 23. So he was able to come up with a relationship between the orbital period of the planets with the distance of the sun, distance of the planets from the sun. He was able to see a very clear connection between them. So based on his law, he was able to quickly deduce that the closer a planet is, the faster it orbits, the farther away from the sun the planet goes, the speed drops significantly. The speed of orbit drops very significantly. So the first two laws of Kepler was concerned with a single planet, that it is an ellipse and it sweeps out equal areas in equal time. The third law was connecting orbital period of a particular planet to its distance from the sun. Okay, this third law would be of major significance in the events that follow this 1619. And now in 1633, Galileo, by this time he had propagated the idea of heliocentrism so much, and he was literally almost like, more people started taking the idea of heliocentrism seriously, and that was when the church was able to take note of this, and they actually warned him and then put him under house arrest for the rest of his life. Look, though this thing is not necessarily relevant to our story, I'm just telling you how the situation was. Someone like Galileo, who was right, we know, and was put under house arrest for the rest of his life for being like curious about nature. So today we don't have that situation. No one is going to be jailed if you come up with a new hypothesis or a radical view of the world. But back then, that was the scenario. Okay, so I'm just telling you the comfortable times that we live in today. So now, in 1680, now I'm just introducing you to a mystery man. Okay, so he predicts the orbit of a celestial object. It is not the mystery object. Okay, by the way, in 1680. There's a celestial object that was observed in the sky, and this mystery man predicts, was able to predict when it would be visible and what was the trajectory and things like that. Eventually, that object would be named after him. Okay, but nevertheless, I'm just telling you this just for you to remember the date. So now, in 1682, the mystery object that is in the pivotal point of a story. Like right now, I'm showing you that this object to be the same, like 1531 and 1607 and 1682, but none of them who observed back then knew what it was. Okay, they thought it was a different celestial object, and it was Edmund Halley who observes this mystery object in the year 1682. Okay, and again, he was obsessed with these celestial objects and how they moved and what was their trajectory, and he was, of course, it was one of his passions to study this celestial object, apart from so many other scientific disciplines that Edmund Halley was involved in. So now we come back to where we started. So 1684. So I hope you guys remember the first slide of the session today. In 1684, there were three great minds who were sitting in a coffee room, probably somewhere in United Kingdom, and they were discussing the big question. So just to remind you, those three people were, one was Christopher Wren. He was an astronomer and a very famous architect back then. And Robert Hooke, known for his Hooke's law of elasticity and the microscope and coining the term cell. And of course, he was also known for his works on planetary motion, his understanding of it. And then we have Edmund Halley, who just a couple of years before this meeting had observed this mystery object in the sky. So now the big question was this. The question was around the Kepler's third law. Okay, so all these people had read through all of the works of Copernicus, Galileo, and people before him, and including it culminated into the works of Kepler. Now, Kepler's first law says that orbits are elliptical. Second law says that they sweep out equal area and equal time if the orbits are elliptical. Third law says the square of the orbital period is proportional to the cube of the semi-major axis, or the distance from the sun, okay, of the planet. So now this third law, it was very intriguing for these three people, and it is not very clearly known how this idea that I'm about to say came about, but it was sort of started mushrooming. The idea started mushrooming among the scientific community back then, Edmund Halley being one of them, is that if the third law of Kepler is true, then there should be a force that is acting on the planets that is directed towards the sun, and that force will be dropping inverse as a square of the distance between them. So if the planet, that is to say, you guys know of the universal law of gravitation. The force of gravity between two objects is inversely proportional to the square of the distance between them. If an object is 2 times farther, the gravity strength drops by 4 times. If an object is 8 times farther, then the strength of gravity drops by 8 square times, 64 times. Okay, so this sort of knew or had a gut feeling or a sort of a sense that the force has to depend on inverse square law of the distance. Okay, now the problem was this: though they have this feeling, they were never able to mathematically prove. Look, this is the most critical part of thing. They were not able to mathematically prove that if the force is directed towards the sun and if the force had a followed the inverse square law, the orbit can be elliptical. The orbit can be elliptical if the force followed these parameters is something that they could not demonstrate. Okay, and that was the burning question. And it is reported that Christopher Wren offered them great gifts, like, if one of you two, Edmund Halley or Robert Hooke, if one of you guys can prove this or demonstrate that the orbits will have to be elliptical if the force followed an inverse square law and the force is directed towards the sun. Now, Robert Hooke immediately goes on to say, no, I've already proved it. I always knew that it followed an inverse square law, and I also have the proof that it follows elliptical orbit. Now they demand him. The Christopher Wren and Halley, I'm not going to give you the proof right away. I'm going to make you wait for a couple of months so that after 2 months, I'll give you the proof so that you know the value of it. So in the meantime, you guys can try to figure out if you guys can do it by yourself. Now, challenge was accepted. Edmund Halley was also obsessed with this problem of, proving the orbits are elliptical. And 2 months passed and not a word was heard from Robert Hooke. And 3 months passed, 4 months passed. Robert Hooke was out of touch, like he did not communicate back at all on his proof. He did not bother. Okay, so now after 7 months, Edmund Halley was tired, like he could not wait anymore, and this question bothered him for a long time. And it was in 1684, the month of August. This meeting happened in the month of January, by the way, the Christopher Wren, Robert Hooke, and Edmund Halley. So nearly 7 months later, in the month of August, Edmund Halley would go on to meet another person. Okay, the historic meet. Edmund Halley travels from London to Cambridge to seek the help of a mystery man, the man that I referred to in the previous, I think, couple of slides before, who observed a celestial object in 1680 and predicted its orbit. So he knew of this mystery man. He knew of his genius. He knew this guy was peculiar, but he knew also that he might actually be the man who could help him out in solving this problem of ellipses. So now Edmund Halley gets on a journey, August 1684, to meet this mystery man. So now, so now he goes on to meet Sir Isaac Newton in 1684. He's our mystery man in 1684. Now, it must be noted that it's very interesting to know of the role of Edmund Halley, which I'll eventually say. But one of the principal thing that Edmund Halley was able to do is this historic meeting between Sir Isaac Newton and him. Of all the other scientific discoveries that Edmund Halley was able to make, his work in astronomy or meteorology, whatever it is, but this particular meet turned out to be one of the most important events in the history of science or physics. So now he goes to Sir Isaac Newton and he proposes this problem. And Isaac Newton says, yes, I have also been pondering over this problem. I've also read of Kepler's works, the third law. And Newton says, I've already solved this problem. So he says, in fact, the question in exactly same words was put forward to Newton. What if the force is directed towards the sun and it followed an inverse square law? What kind of a curve would that follow? That was the question Edmund asks Newton, and he replies without any moment to think that it would be an ellipse. And this answer did surprise Edmund, and he was asking him of the proof. Okay. And Newton said, like, I don't have the proof with me right now. I think I misplaced it somewhere. I worked on this problem some 15 years ago. He says 15 years ago. So I worked on this. And it is also interesting to note that 15 to 20 years ago, which is 1666, 1667, that was the time the United Kingdom had the Great Plague. Okay, the 2 years, a significant population of the United Kingdom was wiped out because of the plague in 1666 and 1667. Around that time, where Isaac Newton had to spend all of his time alone at home, and that was the time he was able to come up with a lot of mathematical techniques and study about the celestial objects. Yeah, so he says I solved it 15 to 20 years ago, but I somehow misplaced it. And then Edmund Halley is like, okay, I think he's going to be another Robert Hooke. He's not going to give us the proof. But Newton assures him that I will definitely work on it again and send it to you in a few months' time. And Edmund Halley was happy that at least Newton agreed to giving, but he was still not sure if it becomes another Robert Hooke kind of thing. Another 2 months, I don't hear from him. In fact, after going back, Halley waited for a couple of months. He still did not receive. It was in the third month after the meeting, early in 1685. I think it was in February 1685, somewhere around that time, that Newton actually sends across the proof that what Edmund Halley demanded for. And there is Edmund Halley sitting in his chair looking at the proof that was submitted by Newton. And when he saw the proof, and as he's reading through the proof, he knew there was something great that he was holding in his hands. He knew that the science was never going to be the same again after that particular set of paper that was written by Newton. He knew that greatness lay ahead. So now he reads it and he was astounded at the way Isaac Newton was able to prove that it was an ellipse. Of course, it's a more complex proof. Even I have a copy of the translated version of his book, which I'll eventually talk about. But he was surprised, and now he immediately rushes to Newton and asks him, like, no, this book is amazing, and I think you will need to publish it as a book. I think everybody needs to know what you have done in terms of this analysis. And Newton now. It was like something was sleeping inside Newton, and suddenly Edmund Halley has woken that dream or whatever was sleeping inside him, woken him up. Now Newton was hooked on to this problem. Now Newton says, Edmund, no, I cannot submit this paper right now. I need more time. I want to refine my work. I want to do more of the study. I want to connect this to in a more general sense. So I need more time. And of course, Edmund had to give in, like, okay, you take your time. Now, Edmund rather would have to wait for another 18 months, okay? For another 18 months until 1687, where Newton is able to work out the entire motion of objects. So now, it is not, so from just solving a particular problem of ellipses, now Newton has come up with a book that talks about all, like, general motion itself. It's not just a force of gravity. He talks about any object subject to any kind of a force, how would that behave? Like, you guys know of this formula, F is equal to ma, force equals mass times acceleration. That force is not just the force of gravity, it's any kind of force. It could be electrical forces or magnetic forces or strong nuclear force or weak nuclear, any kind of force, okay? Including the force of gravity, will have to obey this mathematical principle, a set of equations, okay? So now, he formulates his universal laws of gravitation and universal laws of motion, building upon the works on Kepler and Galileo. And this would eventually turn out to be the most influential book ever written in physics. I will probably show the book at the end of this session. I have a copy of it. I don't know if it's close by, but I'll show it. So now, Edmund Halley looks at it and he's like over the moon, like he's like way beyond satisfied with what Newton had done, and he immediately rushes to the Royal Society, Royal Astronomy Society, I think it's the Royal Society of Science probably, where he goes and recommends that this book be published. And I think it was later decided that this book would be published at the own expense of Edmund Halley. So Edmund Halley took it upon him, revised the book, checked the book, looked for any errors. He did put a great deal of effort in going through the entire set of works of Newton and eventually get it published in the year 1687. Again, like I said, it's one of the most significant contributions of Halley is not his own contributions. Of course, nevertheless, those are important, but his persuasion to make Newton bring out the best out of him. So now this book called the Philosophiae Naturalis Principia Mathematica, or the Philosophies of the Natural World, was published in the year 1687. So again, even till date, it is one of the most influential books ever written. Now, Edmund Halley, now he's again obsessed. His obsession with that mystery object always existed. Okay, he was always wanted to study about that particular celestial object, and the ones similar to that also. So now he comes up with the book. Okay, the synopsis of the astronomy of comets. Again, I'm revealing to you as a comet here. By this time, I'm sure you know what the object is. All of you would have known it. So Edmund Halley writes a book, a synopsis of the astronomy of comets. And now his book was based on his understanding or study of the comets based on what Newton had written in his Principia Mathematica book. So he understood, okay, based on the analysis of these comets, he was able to understand that the comet cited by Appian in 1531, the one cited by Johannes Kepler in 1607, and the one cited by himself in the year 1682, they all had remarkably similar orbits. They had extremely similar orbits. And he also knew that those orbits were not parabolic, or they were not in a straight line. Even Newton himself thought that the orbits of these comets are either a straight line or they are parabolic. They never knew that these comets could come back again and again, visit the Earth. So even Newton himself, who made a prediction of the orbit, assumed the orbits to be parabolic. Kepler himself, they had seen the comet. Kepler had seen the comet right in 1607. He thought comets were like a celestial object that were moving almost in a straight line, never to be seen again. That they were something that originated outside of the solar system. They moved in and moved out of the solar system. So it was Edmund Halley, based on his analysis of whatever Newton had worked, that he observed that the comet's orbit of this particular comet that was observed in 1531, 1607, 1682 was so remarkably similar that he said he was like trying to predict it, guess that they should have been the same comet. And if that were true, then he predicts the return of the mystery object in 1758. Okay, so that was the most critical element of his discovery in that book, Synopsis of the Astronomy of Comets. Of course, it was not just this comet that he was studying. There were so many other comets also that was analyzed, that was taken for analysis in that particular book. But this was the great prediction that Edmund Halley did. So again, 1758 arrives, but Edmund Halley is not there. Edmund Halley dies in the month of January 1642, 16 years before the prediction of his comet would occur. So he knew that he would not be there around when Halley's comet returned, because he knew he died when he was very old, probably 80 or 85. So he knew that he would not be around when, if at all his prediction is true, he would not be there around to see it. But he hoped that if at all it returned, that he would be taken notice of. His prediction would be, given due credits and notice of. And of course, people knew of this prediction, and everybody was prepared to observe if the comet returns in the year 1758, and it does so with great accuracy. The mystery object does return, and of course, it is now famously called as the Halley's comet. And it is not, of course, in this story, some of you, I'm sure you have guessed already, it's not a mystery object anymore. In 1758, Halley's comet occurs in the sky on the eve of Christmas. Okay, it was the Christmas time. It appeared around December 25. Okay, on that day. So now it is not just that the accuracy with which Edmund Halley predicted, it was the first vindication of the genius of Newton. It was the first vindication of his book that was published in 1687. The first major experimental evidence that the nature itself was the lab and the experiment was the comet. The prediction was a great vindication of whatever work that Newton had done. Okay, so again, now with this prediction, Newton forever changed the way people look at science. Okay, until Newton's time, it was not very clear what was the laws that nature obeyed, what was the way in which what was the way to predict the nature's behavior. Now he forever settled it. It is in the language of mathematics. The nature can be explained through the language of mathematics. It was his equations that helped predict things. It was his equations that helped predict the return of the Halley's comet or anything for that matter. So he wrote down, forever changed the idea that the nature can be written down in the form of equations in the language of mathematics. Okay. Now remember, Kepler was also came up with equations. Okay. Kepler's laws were also equations, elliptical equations, and the third law particularly was an equation. But Kepler's laws or equations came after observing the data. It is sort of what you call as a fitting the data. It is like an equation that would fit the data. Okay, it does not come from first principles. The result of the equations has not come from the fundamental understanding of something. I see a set of data and I try to fit an equation that would agree with the data, and that is how Kepler had done it. But what Newton had done was he had his fundamental postulates and hypotheses about how the orbits would be elliptical and the force would be the inverse square law, and his three laws of motion. Those set of fundamental understanding would eventually give rise to Kepler's laws. He was able to come up with Kepler's laws even without any data. So that is the brilliance that Newton was able to do. So it might look like, okay, if we're able to arrive at Kepler's law without any data, then is Kepler's work of not any use? No, of course not. It was Kepler who gave the data in the first place and gave an idea or motivation for Newton to work towards it. So now it is interesting to see a set of equations that come from fitting the data. Also, the same set of equations come by deriving from first principles without any data. Isn't it a beauty of science? I mean, this is the beauty that Newton was able to make. And of course, that brings to the end of my story. Of course, with Halley's comet, and mostly Halley is known for, the moment you think of Halley, you think of Halley's comet. Last it was visible in the year 1986, but unfortunately I was not around. I was born in 1988. I still regret not being able to see Halley's comet, but it's going to arrive back in 2061. Again, the predictions are better now and we can predict with greater accuracy today. And in 2061, hopefully we'll be around to see the historical comet that was observed by the greats of Kepler and Edmund Halley and Airp, and we hopefully will be able to see the same comet again that was observed by them. But just as a consolation, I think in the year 2020, in the month of July, we were able to find another comet. That was the comet Neowise, and I was lucky to have observed it and have imaged it. I have other images of this comet Neowise as well, but you can see this the beautiful tail of this comet. Of course, it was in the twilight condition, so the second tail, the ion tail, is not visible here. But yes, again, at least I'm happy that I've seen one comet in my lifetime, but I would certainly want to see Halley's comet as well. But the story of gravity does not end here. Okay, the story of gravity is just began. It was Newton and Edmund Halley, yes, and eventually there are so many other things that vindicated Newton's theory. For example, the discovery of the planet Neptune, because the orbit of Uranus had some anomalies. So in order to fit the data of Uranus, they predicted there could be a planet number 8, which is Neptune, that could be the cause of the disturbance in the orbit of Uranus. And they rightfully, based on the predictions of Newtonian laws, they were able to predict and find the planet Neptune. Again, William Herschel and Le Verrier, there were so many other people involved in it. Those were all, like, we had, what I'm trying to say is we had several other evidences and observations that reinforced the idea of Newtonian understanding of gravity. But Newton, in all his time, he never explained what was the cause of gravity, what was the reason behind gravity. Okay, he just came up with the equations that will tell how something under the influence of gravity move and giving us way to predict it. Okay, so that is still one of the a lot of things that understanding of the cause of gravity still exists. But now, until about several hundred years later, this notion would not be challenged. This notion of gravity would not be challenged. But I'm sure you guys know who was the other guy who came in and changed our, not changed our understanding, but rather took our understanding of gravity to another plane above, one step above, and that was Albert Einstein in 1905, the miraculous year where he came up with several papers, 4 to 5 papers, where he thought of gravity as a consequence of the geometry of space-time. That is exactly completely a different view of the universe. And of course, this is not to say that Newton was wrong. In special case where in our everyday scenario, the equations of Einstein will reduce to equations of Newton, but he was able to cover the boundaries, extend the boundaries in which the equations could be applied. So it was in 1905. Again, it would take another journey altogether, but I'm not again going to cover in this story, but I hope. So next time, I think I took almost an hour, probably more on this story, but I hope you found this interesting. Next time when you look at the equations, the 3 laws of motion or the Kepler's laws of planetary motion or any sort of things, universal law of gravitation, just remember there's a lot of things that has gone behind it. It is not just 2 lines or 3 lines or a bunch of equations that you see on the book. Several minds, several geniuses, several fights, emotions, a lot of things have gone behind it before you can see them on the book. And that, to me, is more like exciting and inspiring than the equations themselves, because I value those equations even more now. Those are not just equations. They talk about an entire history of what kind of genius were involved in it. So that, I think, is what I would request you guys to look at in any of the things that you learn. And I think I would end on that note. And yes, I stop my screen share. And if you have any questions, please do let me know. I'm open to take questions. Hello? Or was I audible, or the entire session was like in mute? That would be interesting. Okay, I think
Audience can post their questions.
yeah, if you can read out the questions, it will be great.
Yes, sir. What is your view on Oumuamua object?
So that is a very difficult name to pronounce. Yes, of course. That was an first interstellar object that the scientists observed. The orbit of that was extremely eccentric. And also the velocity, the speed of the object was so high that they thought it was an interstellar object, and it is the first known or interstellar object that visited our solar system, at least in our times. So there is no my view on it. I just know this much, that they were able to study this orbit, and the shape of this object was very peculiar. It was a very slender, thin, and long. Like, that it's a very peculiar shape. I know it's still irregular, but still it's a very peculiar, long, slender shape. But that's all I know of it. And I don't have any more things to add about that particular object.
Anyone else have any other questions?
Yeah, please do.
So I think no one has any questions. So how could we get a soft copy of the English version of the Principia?
Oh, okay. Let me. I told to show you the. Give me a moment. I'll show you the book. I'll try to get the book. But a soft copy, I don't know. But either ways, it is difficult. Let me turn on my video to show you the book that I have. Can you guys see it?
Yes.
So it's the Principia, the mathematical principles of the natural philosophy. And I think it is reprinted in 2010, but I'm not sure. I'll probably check the online version and if any PDF is found. So, okay, let me tell something about this book. Look, first of all, this book is extremely difficult to understand, okay, because he doesn't use calculus explicitly in this book. So, though his ideas of calculus are seen here, he uses mostly geometry, plain geometry to explain. Even his proof of ellipses, that the force directed towards the center of the sun and inverse square law, the proof that such an orbit will be elliptical is completely through plain geometry. No, but of course, though it is just plain geometry, the understanding of it is more difficult. So if you see his book, it is full of like all these geometrical drawings. Let me see if I can show you some page of the ellipses. Okay, just let me show you. So if you look at this particular image, so his book is full of such geometries, and he uses his insights and brilliance is like way too beyond our comprehension. But however, if you're interested in understanding this a little more, there is another book by Feynman, okay, which I have a copy of. It is The Motion of Planets Around the Sun by Richard Feynman. So this book is all about proving the law of ellipses, okay, but again, it is inspired by the works of Newton, but Feynman takes a different approach. But again, this book does the proof of ellipses without any calculus or complex mathematical operation. It is full of geometry. He tries to analyze the motion of planets around the sun geometrically. Again, this is a very interesting book. I think you can find this book online. It is by Richard Feynman, The Motion of the Planets Around the Sun. So again, this book I'm sure is easier to find online. The asteroid 2020 maybe. Yes, I read the question. And the asteroid 2020, right? Yes, one of the challenges in being prepared for such an asteroid, I assume, is that how quickly are we able to know of its existence? Okay, so some of these asteroids are very small that not until they are few days before they fly by we know of it. Some of them were able to track for months and years together. So in terms of being prepared, I don't think we still have an idea. The one thing is like sending a mission to it where we can actually forcibly change its trajectory that it could miss Earth if its trajectory is actually towards Earth. But apart from that, then the more dramatic way of blowing up an asteroid, just like the movie in Armageddon, is more unlikely because to break up an entire piece of rock and to go there, land on it and plant it. Or maybe there's another thing that you could fire from Earth. Again, all this looks like science fiction, but there's only one thing that you could do. Either change its course from being colliding with the Earth, or like break it apart into pieces small enough that even if they come to Earth, they would burn up on Earth's atmosphere. So, that's the only two options. And I'm sure people are looking at it. Yeah, asteroids. I'm sure recently you've heard of this RCBO observatory that went down. That was one of the primary observatories that were tracking the asteroids for a long time. But I'm sure there are other observatories observing it as well. But yeah, I think this will improve in the coming years, the tracking of asteroids. Does that answer your question? I mean, that's all I know. I mean, on that particular question. There is a question on documentary. Okay, I'll send this documentary links to the books, online links, if at all. I'll send it to you on Telegram, then probably you can share it with the students.
Yes, sir. So, what is your opinion on Feynman's lecture of physics?
I mean, that is like, I mean, I don't have an opinion. I'm inspired by him. I have his lectures of physics as well. It is one of the books that inspired me. I can show you. This is volume 2, lectures on physics. So if you're interested in physics, please read Feynman's lectures. It is not just the equations that are being explained in a very easily understandable way, but it is his mind that you can get to see how was Feynman able to think of these things. That is just mind blowing. And to me, my inspiration for the subject physics is Feynman. So yes, Feynman's lectures of physics are one of the finest pieces of book that we have, and I would request all of you to read those books. Which would you recommend to learn astronomy from beginning to advanced level? So my journey into astronomy was mostly through physics. Okay, it was like physics. Then I stepped into astronomy. So I had um, books on like some of the books written by Carl Sagan, for example. I mean, if you want to learn astronomy at the beginner level, first thing would be to get interested in the subject. Okay, so any book that can make you interested in the subject, like Cosmos. Yes, Cosmos is a very good book. Then you have The Pale Blue Dot by Carl Sagan, and there are books like by Neil deGrasse Tyson, like The Universe Down to Earth. There are these generic books on astronomy that gives you a sense of what the subject is about in general, and also pulls you into the subject enough. And then you could get into more technical books. Okay, and as far as technical books are concerned, I do not have the list with me right now, but I'll again send those links. But Cosmos, The Pale Blue Dot, are really good books that can get you hooked on to astronomy as a subject. The Pale Blue Dot, I'm sure you know, but I'll type it out anyway. By Dr. Carl Sagan. Yes.
So I think that's all with the questions, sir.
Thank you.
So thank you, sir. That was an interesting and insightful session. So on behalf of SEDS KCT, the entire crew behind the event, we are immensely thankful for you to join us. So,
Thank you.
And last but not the least, I thank all the audience for showing up in great numbers and gracing the occasion. Oh, thank you, sir. I request the audience to fill up the feedback form so that you can receive your certificates.
Thank you very much for this opportunity, and looking forward to interact with you probably sometime later as well. Thank you so much.
We are also
See
looking
you
forward.
soon. Yeah, bye bye.
Thank you, sir.
Thank you.
Thank you, everyone.